Okay, so we are starting our next unit, which is called heat or thermochemistry. And it's one of my favorite units because I feel like you can see it all around you. Heat transfer is happening all of the time, and a lot of that is intuitive. Um, People find this unit challenging though, because everything really builds on something else in the unit, and it's a rather lengthy unit. So you want to make sure that if things aren't clicking, you're getting help right away. Another thing to keep in mind for this unit is that the vocabulary actually matters a lot. There's some words that you might think are kind of the same or close enough, but you want to pay really good attention to what each word means. And also with the units are going to matter as well. So looking at heat. Heat is a type of energy. In the last unit, we looked at, or we talked briefly, I guess, about how you can have a solid turn into a liquid and turn into a gas, go through all those phase changes by adding heat. And what that heat does, it gets the molecules to move more, it overcomes some of the attraction between them, and therefore they can separate. It relates back to the first law of thermodynamics that you also have maybe heard before, that energy can't be created or destroyed. But it can change form. So heat is one type of energy. Motion, kinetic energy is another. And when we are heating up those molecules, getting them to move more, we're just using that heat energy in order to get the molecules to have some more kinetic motion energy. So you can equate in your mind the word heat and energy. Just know there are other types of energy as well. What is not the same is heat and temperature. So heat is not the same thing as temperature. Temperature technically is the average kinetic energy within a substance. If you ask me, oh, how hot is your coffee? You're asking me for the temperature of the coffee. You want to know a measure on average of how fast those molecules are moving. Whereas when we're talking about heat, energy, we're talking about flow. You can heat something up, you can cool something down by removing heat. So heat is that energy flowing through to or from the object at hand. Heat and temperature, not the same thing. So the first thing we're going to do, and a lot of the problems we're going to solve at first, are looking at how heat being transferred, that flow of energy, can affect one system or its surroundings. And so if you think about heating something up, think about what matters. It matters how much of it we have. Are you talking about heating up a little pot of water or a huge pot of water? You know it's going to take more heat energy to heat up to get to the temperature you want in that big pot of water. It also matters, what is it that we're heating up? What object? Let's say we have a plastic fork and a metal fork outside. We're picnicking. And it's a nice, warm, sunny day. And we've been sitting around for a while, and then we go to eat. You know, without me explaining why, you know you'd rather pick up the plastic fork than the metal fork, because that metal fork, if it's been sitting out in the sun, you know is going to be really hot. Now, the metal fork, the plastic fork, they've both been sitting outside under the same sun for the same amount of time. But because of the material, the difference between whatever metal the fork is made out of versus whatever plastic it's made out of, different materials will absorb that heat differently. And then finally, how much are we trying to heat something up or cool something down? How much of a temperature change is occurring? And so if I combine all of these things into the formula we're going to use, that formula looks like Q equals mCpΔT. Now, I wrote it really far and spread out, but that's because I wanted you to see how much we're looking at the mass, what mass, which we measure in grams, the units for mass would be grams, what mass are we heating up or cooling down? What object, right? Is it the plastic fork, the metal fork? Is it water? Is it totally depends, because different objects heat up or cool down using different amounts of heat. That's something we call the specific heat. We'll come back to its units. They're the ones that always look funky. but I'll show you why. And then how much did the temperature change? Delta is that triangle. Delta means change. And then capital T, always a capital T, the change in temp. In the gases unit, which is the last time you worked with temperature, everything had to be Kelvin, had to be Kelvin, had to be Kelvin. Because of how change works, it doesn't matter if you're looking at Kelvin or Celsius here. Most of the time, things will be in Celsius because that's what our thermometers in the lab would read. So expect Celsius, but Kelvin is also okay, and we wouldn't have to do any conversions between the two. And then, keeping in mind what were all of these things? Why do we care about how much or what it is or the temperature change? Well, that's what the Q represents. That's saying how much energy, or you can say how much heat. We give a certain amount of heat to an object, depending on what that object is, how much of it we have, it'll change temperature by a certain amount. Same thing with taking heat. Cooling something down is just removing heat. So energy or heat, what the unit we tend to use the most is joules, Joules. It's a capital J. We could also use kilojoules, which is a lowercase k and an uppercase j. Just like grams and kilograms, you could convert using King Henry. Same thing with joules and kilojoules. And then also, we tend to not use it so much in this class anymore, but calories. When you look at a bag of chips and it tells you how many calories, that's telling you how much energy your body is going to get from eating that food. Bags of chips in other parts of the world don't say calories on them, they say kilojoules, but just another unit for energy. So calories, kilocalories are also a thing. Again, the vast majority of the time we'll be working with joules. Okay, so I had avoided telling you the units for specific heat up until now. Some of you might be able to figure out once I give you the units where they come from. But oftentimes our units for specific heat are J over G degree C. So that would be joules per gram degree Celsius. But sometimes they could be joules per gram Kelvin, or calories per gram Kelvin or degree Celsius. Those units always sort of have to match the other units throughout the formula. So for instance, most of the time I told you we're working in joules. If I plug in joules for my heat, my specific heat should have joules in the numerator. My mass is always going to be in grams. We'll always have grams in the denominator. And then again, it doesn't matter if you plug in Celsius or Kelvin because we're always looking at a change. But you would specify whichever units you actually used in that formula. So those are the ones that look a little strange, but you can always figure them out based on the other units in the formula. Now, we look at water a lot when looking at heat problems. Part of that is because water is used in so many places in life, but also water is really, really, really good at absorbing heat. Part of the reason some nuclear power plants have water surrounding them is because that water can absorb a lot of heat before it boils and vaporizes compared to other objects. And so it kind of is in there as a fail-safe in case anything bad were to happen. The reason like you have a swimming pool and it's out in the sun and some of you use heaters on your swimming pool is because even on a bright, hot, sunny day, that pool might not be as warm as you want it to be because that's a lot of water. And water takes a lot of heat to heat up. That means water has a high specific heat. So the specific heat technically is how much energy, how many joules do I need to take 1 gram of that substance, in this case water, and change its temperature by just 1 degree Celsius. Water's specific heat is 4.18 joules per gram degree Celsius. Whereas, for instance, some metals have a value of like 0.4 joules per gram degree Celsius. So water is really good at absorbing heat comparatively. You'll always be given water's specific heat value. And those units on it tell you what units everything else in the formula need to be in. This is specifically for liquid water. Solid water, gaseous water, we'll look at next time. Also for water, it's important that you know the density of water is 1 gram per milliliter. So I'll give you that, but really what that translates to in a practical way for you is knowing that if I have 1 gram of water, it would have a volume of 1 milliliter. If I have 1 milliliter, it would weigh 1 gram. So this formula that we're using, Q equals mCpΔT, has mass in it, but sometimes I'll just tell you, oh, we're using 45 milliliters of water. For water, because its density is 1, that's the same thing as me telling you we used 45 grams. Okay, I'll write this formula neatly and compact. The m, Cp, and delta T are all multiplying by each other, and we'll do a couple of sample problems. Okay, so we're going to do these 2 sample problems. You can see I wrote the formula on the right for you. Q equals mCpΔT, and all the other information you'd always be given. Again, keeping in mind the words matter, making sure you know the difference between heat and temperature, for instance, where they get plugged in, and so do the units. So what I suggest is as you go through the question, let's underline things and label what variable they would show up as in the formula. So for instance, find the energy. Find the energy, that means I'm solving for Q. Q is energy or heat. I could have used the word energy, heat, it doesn't matter. Absorbed by 200 grams, that's a mass of water. Why does it matter that it's water? Well, the fact that it's water tells me I know its Cp, its specific heat, is 4.18. And it's warming from 12 to 46 degrees Celsius. That's going to help me find my change in temperature. The way we teach this is probably slightly different than how you'll see it on lots of other YouTube videos. I think it's really helpful for lots of reasons. Trust me for now. When we're doing our change in temperatures, always just do bigger minus smaller. You're going to need to be able to think through, is it heating up or cooling down anyways? So if you just always use positive change in temps by doing bigger minus smaller, I think that'll make your life easier in the long run. So how much did the temperature change? Well, it went from 12 to 46, or I can find the change by doing 46 minus 12, and that would get me a change of 34 degrees Celsius. So I want my Q, maybe I should say, put a question mark next to it so I know that's what I'm looking for. I have my mass, it's water, so I know my Cp, and I just found the change in temp. I can plug in and solve. Q equals m Cp delta T. I would plug the 34 in here. I'd do that subtraction separately rather than plugging in the 46 minus 12 in case you just plug in your calculator wrong because of that. Multiplying it out, 200 times 4.18 times 34, that would get me 28,400. And you need to know that that's in joules. How I know it's in joules? A couple different ways. Number one, I solved for a Q. And so heat, energy, we typically measure it in something like joules or calories. Why is this joules rather than calories? Well, the Cp I used for water is 4.18 joules per gram degree Celsius. Therefore, my value came out in joules. I could ask you to turn it into kilojoules, and then it would be using King Henry. So I currently have joules. I want to get to kilojoules. That would be moving the decimal 3 times to the left. So I could say 28.4 kilojoules. Again, you don't always have to do that. I just want you to realize how the two values are related. Either answer would be fine, 28,400 joules or 28.4 kilojoules. Okay, next question. Again, I'd say let's look at all the information we have. So 50 milliliters of water. Since it's water and the density of water is 1 gram per mil, I know that 50 milliliters really means I have 50 grams also, and that's my mass. Since it's water, again, I know the Cp is 4.18. In some of the try problems you're going to do, it won't be water, but you'd be given a different Cp or you'd be finding the Cp. And it says it is, I'm changing colors just so I don't get lost in here, initially at 30 degrees. Initially at 30 degrees is not the change. I have an initial temperature, but I don't know how much it's heating up or cooling down. So I'm going to keep that in mind. We can actually say Ti for initial temperature is 30, but that's not something I can plug in anywhere. So again, reading these words carefully matters. It absorbs absorbs 2,200 joules of energy. Since it's absorbing heat, if you think of heat as like a present that I wrapped up and I gave it to you and you absorbed it, I know that's absurd. Everything the way I teach is absurd. When you absorb heat, your temperature goes up. Your temperature is going up because we absorbed heat or energy. How much heat or energy? 2,200 joules. That means my Q is 2,200 joules. So I'm kind of organizing my information a different way here. I'm writing out what everything equals. Whatever way works for you, but don't just read the question and then think you're supposed to have it all figured out. Calculate its final temperature. So we're trying to see, okay, we know it starts at 30, we know it's heating up. We don't know how much it's heating up, but that's what we're looking for, is what's its final temperature. So given all this information, I have a Q, I have an M, I have a CP. Plugging in what I have, let's see if that helps me find something that is important or valuable. 2,200 joules, that's my Q. My mass was 50. My CP was 4.18. It's gonna let me solve now for my change in temp. So I'm gonna do, if you wanna do 2,200, if you wanna do the 50 times the 4.18 first, you can. You get 209. Take the 2,200, divide by 209, and we'll get a change in temp of 10.53. Started at 30, we are going up because it absorbed energy. We're going up by 10.53 degrees Celsius. To find the final temperature, we add them. If it had said we removed or that the heat was released, that would be how we would know that the temperature was going down. So absorbed, warmed, temperature is going up. Released, I already forgot the other word I used, but temperature would be going down. The try problems are, again, slightly different. They're not carbon copies of this, but you have your formula, see what you can plug in where, and just read the words carefully. Ask for help if you need it.